So in this section, we're going to start our journey into multi-agent systems. Now, let us begin by developing the right mental model to approach multi-agent systems in LangGraph or multi-agent systems in general. Now, imagine that you have a house and you need to fix a light bulb. You need to fix your light bulb. So the task is to fix a light bulb. Let me get this to medium. So fix a light bulb. Yeah, that's the task. This is a single task, and you probably don't know how to do it. So what do? You call an electrician. So you simply give this task to an electrician. Let's pull that up a little so that, yeah. So you give this task to an electrician. The electrician definitely has knowledge about electrical fittings, fixing electrical stuff, and he comes around with his tools and helps you to fix your light bulb. Simple and straightforward. Now, that's what we've been doing so far. We have been building single agents, specialized agents that perform one task. So you have a task, and you give it to an electrician. And that electrician comes with his tools, with his knowledge, with the instructions you have given the electrician, which is your prompt in this case, and he gets the task done. Light bulb fixed. That's a single agent. One LLM instance with tools, or can be multiple LLM calls with tools, a system prompt, and a conversation history. And everything happens in one context window, one decision-making loop. That is what a single agent does. A single specialized agent, just like the one we have seen with the create agent, react agent. You build an agent that is specialized to perform one task. Now, what if you want to renovate an entire apartment? You want to renovate your entire apartment. That is not one simple, straightforward task. So now the task is to renovate apartment. So you need to renovate your apartment, and part of the tasks involve electrical work. There's going to be some plumbing work. There is going to be probably some woodwork. You might want to have POP fittings. You might want to have a garden outside and all sort of stuff. So despite this being a single goal, which is renovate apartment, it consists of several tasks. And most likely one person is not going to handle all that task, except you have a G.I. Joe handyman that just knows how to do everything. But no, most of the time you will need to delegate to different experts. So for electrical stuff, you call your electrician. For plumbing tasks, you call a plumber. For gardening tasks, you call a gardener, and I'm sure you get the gist. You call a gardener. So you call these guys, and you delegate tasks to each of them. Each of them have their own set of instructions. Each of them come with their own set of tools, and each of them have their own area of expertise. This is how a multi-agent system works. When you have a goal that involves several specialized tasks, you need to build a multi-agent system. And with a multi-agent system, you get to break down this goal, have multiple agents, each with their own specialized prompts, their own focus tools, isolated context, and all connected through a coordination mechanism. Meaning that you have to coordinate the activities between all these guys. Because some of their tasks can be done in parallel, whereas some of them have to complete their task before another expert can take over. Did I spell gardener well here? No, I don't think so. Let's fix that. Gardener. Yeah. Not gardener. So, sometimes their tasks can be done in parallel. So let's say the electrician and the gardener can be working simultaneously. I don't think it's going to be on rare occasions where the gardener has to wait for the electrician to finish his work, or the electrician has to wait for the gardener to finish his work. But the electrician and the plumber might not be able to work at the same time. You might want to finish your electrical work before you start plumbing, or you might want to finish your plumbing work before you start the electrical work. All these coordination systems, we're going to be seeing them in the way of design patterns going forward. We're going to be looking at different design patterns that can be used to implement multi-agent systems, and we're also going to be looking at how state is managed. So multi-agent systems are all about dividing cognitive labor. Just as organizations divide work among specialists, multi-agent systems help you divide AI work among focused agents that excel in their own domain. So yeah, that's simply multi-agent systems. Next, let us look at the anatomy of a multi-agent system. Before we do that, I'm just going to put this in a frame. I'm going to put everything here in a frame. Yeah, I like properly organizing my stuff, so let's just have all this in a frame. Now, the next thing we're going to look at is the anatomy of a multi-agent system. Anatomy of a multi-agent system. Let me just bump that up a little bit. So anatomy of a multi-agent system. What are the components that a multi-agent system comprises of? Now, the first is agents, for sure. Agents. So we have agents. And as I have described, these are independent units with their own LLM, prompt, tools, and state access. We're already familiar with agents already, so there's no need to go deep into that. Independent units with their own LLM, prompt, tools, and state access. Now, the key decisions that need to be made when you're building your agent is, first, you have to determine how specialized they have to be, what tools per agent, and what's going to be the personality of your agent, and of course, what are going to be the constraints of your agent. So basically your agent's scope. So how specialized, what tools your agent has access to, and also your agent's personality and constraints. The second thing that comprises of a multi-agent system is the coordination mechanism. Now, this defines how your agents work together. From the definition, a multi-agent system consists of different agents working together. So you have to define how they work together. Who decides the routing? How do the agents communicate? What even triggers the transition from one agent to another? And as I mentioned earlier, we're going to be seeing that in our multi-agent design patterns. We're going to be looking at different multi-agent design patterns in this section. So that is all going to become very clear very soon. The next component is state management. State management, very, very important. How do you manage data flow across agents? What information stays persistent across agent interactions? What is shared? What is isolated? And how does context flow through and between your agents? So that's basically what we're going to be looking at in state management. And when we start looking at design patterns, you will see how each design pattern helps you manage state. Lastly, we have entry and exit points. Entry and exit points. Now, basically what this defines is the interface with the users, the people that are interacting with your multi-agent system. At which point do they enter data? Which agent is talking to them? Can all the agents talk to them? And also, how do the agent or agents get to respond? Yeah. Entry point, which agent is talking to them? How many agents can talk to them? Exit point, which agent replies them? How many agents can reply them? So, that's basically the four components of a multi-agent system. Agents, which are the specialized components doing the work. What is your coordination mechanism? Who is making the decisions? How are the decisions made? State management, how does data flow through and between agents? Which data is isolated? Which data is shared? And also entry and exit point, which agent or agents get to talk with your user, and which agent or agents get to respond to the user of the multi-agent system. So basically, that is the anatomy of a multi-agent system. Now, the next thing we're going to be looking at, and I'm just going to create a new frame for that, we're going to be looking at when multi-agent systems make sense. When do you actually have a multi-agent problem? because you don't want to use a multi-agent system when you don't need one. So when does it make sense for you to use a multi-agent system? Let's have that title up there. That will be when multi-agents make sense. Because half of the process of you building an agentic system is making the right decisions. You don't want to over-engineer or have overkills. So when does it make sense to use a multi-agent system? Let me make that extra. Okay, yeah. When multi-agents make sense. First is when you start noticing that you have a tool overload problem. A tool overload problem. Yeah. When you start building a single agent and you start making it godlike, can do everything, and you notice you are having up to 30 tools or more, that is going to confuse your LLM and it will start making poor tool choices. And a lot of times it's going to even start confusing tools or picking irrelevant tools. So once you start having up to 30 tools and more, then you should break things down. You know that you have gotten to an inflection point and you have to actually break things down. Distribute tools across specialists and have if you have 30 tools, break them down into 3 specialists and give each of them 10 tools. Give each of them 10 tools. So when you start noticing a tool overload, that is a trigger that you might have to redesign your system from a single agent approach, from using a single agent approach to a multi-agent strategy. So that's the first thing when you have tool overload. The second trigger to you knowing that, yeah, it's time to introduce a multi-agent strategy is when you start facing context window limits. When you start facing context window limits. Traditionally, single agents use one LLM, so one context window, and quality begins to degrade as conversation grows. Once you start having long conversations with your agent, imagine a user keeping an agentic session on for days, and not just days of being dormant, no, active days. The quality of the conversation would definitely degrade. The agent will start to forget things, to start to miss context. A lot of times, I talk to Gemini and it just gives me the wrong thing. Like, it just starts talking about something I didn't refer to. Like, there was a time I was using Gemini to generate descriptions for my YouTube videos, and I'll give it a topic and it will just go and pick an old description. then I'm going to correct it and I'll be like, oh yeah, sorry, I forgot, yeah, blah blah blah. And also Claude, let me move on the screen so that you know that your screen is not frozen. Claude did something interesting recently. I was trying to resume a conversation and it told me that it is going to compact all our previous conversations because I hadn't talked to it for like 2 days. So it just popped up in a progress bar and the message was compacting previous conversations. And I know what it was doing behind the scenes was that it was summarizing the memory system, because there's this map reduce strategy you can do with your long-term memory and short-term memory, and you can use it to kind of summarize the previous conversations so that it still makes sense for preceding interactions. So context window management is something that you have to deal with a lot. Some models have large context windows. Gemini started giving us 1 million tokens in the context window, even though there are models in Gemini that give 2 million. But Anthropic, I don't think Anthropic has even cracked the 500k limit. Anthropic is always very, very conservative. So I don't even think they've cracked the 500k context window limit. So when you see that, when you notice that for each, as the conversation with a single agent grows, which is, if you see that as a possibility, there's an indication that the context window can grow beyond necessary and you want to split things up. So you do context isolation where each agent works with only what it needs. You break things down and you are able to give different agents different small pieces of the information, subsets of the information, so that they can work on it separately and each one does not exhaust the available LLM context window. So when you start having context window limits, That's another indication that you have to use a multi-agent strategy. Another indication is when you start having sequential constraints. Sequential constraints. From the graphs we've been building, and even from the single agent that we've built using the create agent pattern, which definitely uses the React pattern under the hood, everything just flows. So if we have a workflow and it has point A, point B, point C, point D, everything just flows. But what if you have constraints? What if you have to process A and be done with it, or have a verification check before you can then move to point B? Yeah. What if, for example, in an account system, you have to verify your identity before you get account access, and also maybe you apply for a refund, but they need to verify your warranty before you can get the refund? If you have those constraints, then you might want to introduce a multi-agent strategy, because with multi-agent you can architecturally enforce a handoff from one agent to another agent, or from one step to another step. Agent B will be literally unreachable until agent A completes. Agent B will be unreachable until agent A is done with his task. We're going to be looking at a design pattern later called handoff that is very perfect for this type of scenario. So when you want to introduce sequential constraints, you might also want to consider a multi-agent system. Another indication is when you have strong parallelization needs. When you have strong parallelization needs, if tasks need to run, or rather, if tasks can run in parallel, you should not make them run sequentially. They should not run sequentially. Like using the renovation analogy that we discussed earlier, your gardener shouldn't have to wait for your electrician. Your gardener shouldn't have to wait for your electrician. Your electrician also shouldn't have to wait for your gardener. Why do you want green grass before you can light up your house? So it's unacceptable latency, because independent subtasks can run sequentially. So you can use a multi-agent system to dispatch tasks to specialists simultaneously. You dispatch tasks to specialist agents simultaneously. So that's one more indication. The last one we're going to discuss is when you have organizational boundaries. Organizational boundaries. When you have organizational boundaries, then that's an indication that you should use a multi-agent system. Now, as a rule of thumb, if you are going to be designing any kind of thing that has an organizational structure, you have to go with multi-agent systems. Yeah, you have to go with multi-agent systems. You can't be designing agency and it has sales on one side, it has support on one side, it has engineering on one side, and you're trying to cram everything into a single agent. Now, that's not going to work. So once you look at your task and it looks like an organizational structure, just go with multi-agent system. Just go with multi-agent systems. And also, when you need different teams to support different aspects of your agentic system, for example, you have an agentic system that has a sales department, it has a support department, it has an engineering department. Definitely, you want to devote each agent to different teams in your development team. In your development team, you want to give each agent to different teams. This is kind of like the same heuristics that is used to determine whether you should use something like a microservices system. A microservices architecture is not just something you just pull out as a silver bullet to solve all your problems. Once you notice that the way your application is being built, you need to devote different parts of your applications to different teams, you might want to consider using a microservices architecture. So it's something that it is indicated organizationally, not even by complexity. So each team owns their agent, and you develop a central layer that composes everything. So these are your triggers to know when a multi-agent system is required to do the work. But if everything is still simple and focused, you have like less than 15 tools, if you have tight latency requirements, because multi-agent systems do add their own latency overhead, but if you have tight latency requirements, if you have limited budgets, That's another thing. You have to consider how much resources you have to develop also. And also when you are in early development stage, just go with single agents. Just go with single agents. But if you tick 3, sometimes even 2 of these boxes, you want to consider using the multi-agent approach. Anyway, now let us talk about benefits. Let's talk about benefits. Yeah, I think we can fit benefits in here. Let me see if I can highlight all this. Yeah, good. So we can fit benefits somewhere here. So what are the benefits of using a multi-agent system? The first we're going to be discussing is better accuracy. Better accuracy. Let me take this down a notch, okay? So the first is better accuracy. Specialists always outperform generalists in their domain. Yeah, specialists will always outperform generalists. I think there's this saying I heard that there is nothing that does 2 things that is the best at one of them. There's no component that does 2-3 things that is the best at one of them. So just an anecdotal saying to make you understand that, yeah, you most likely won't be able to outperform someone that is a specialist in their own domain. Yeah, you can't outperform such kind of people. A gynae might know all about childbirth, but if you're going to be going under the knife, you would need a surgeon to come and perform a CS operation. Yeah, so just speaking from some experience there. So yeah, you specialists will always outperform generalists in their own domain. So that's the first thing. The second thing is better tool selection. Better tool selection. When you have an agent that is given fewer tools to work with and has a better understanding of his domain, it will make better choices. That agent is going to make better choices. If you give a generalist agent 50 tools, just be prepared for your agent to go off the rails. But if you give a specialized agent 5 tools, 7 tools, or at most 10 tools, then you get better performance. Then you get better performance. Then you can rest easy knowing that your agent would make better decisions. So that's another thing. Also, there is the case for maintainability. Maintainability. A multi-agent system is going to be easier to maintain because you can test your agents independently. You can test their capabilities independently. You can write evals for them independently. You're not trying to write evals for an entire multi-agent, an entire monolithic agent that does like 50 different things. No, you test. You can test your agents independently. You can reason more about your system compositionally. So that's and like we said, even your team is easier for your team to manage different agents, and you don't have this single point of failure. If one agent goes down, the entire system doesn't have to go down. Which would be the case if you have a single agent that is trying to do a lot of things at once. So yeah, that's another benefit for using multi-agent systems. Another one is parallel execution. Parallel execution. We've discussed that already, so I don't need to say much on that. But like I said, if tasks can be performed simultaneously, don't run them sequentially. That is just taking a latency cost that is very, very avoidable. So you can process with multi-agents, you can process independent subtasks simultaneously. Another thing is what we refer to as graceful expansion. Graceful expansion. Graceful expansion. Now, what this means is that when you have a multi-agent system, you can easily add more specialist agents without destabilizing the entire system. Yeah, you can add more sub-agents. For example, in our renovation analogy, you've called an electrician because you need electrical work done. You've called a plumber because you need plumbing work done. Your gardener is doing a thing. And you want to fix internet. Yeah, you want internet connectivity in your house. You don't have to you don't have to disrupt others. You just add a provider and they will come with their tools and get it all set up. Find some of their tasks can be dependent on the electrical guy, but still you can just add them without disrupting any other person's work. if you had a single, like I said, GI Joe handyman handling everything, and he's currently doing electric work, then you tell him, oh, I need internet connection. He will tell you, you have to wait. You would have to wait. Let me be done with this, then I can move to that. But for a case where you have proper division of labor, you just call the other guys, and you can even use a different provider. You don't have to have the same person giving you electricity, giving you internet connectivity. You can use different providers. So graceful expansion, you can easily expand, you can easily make your system better, and you can also easily remove. Yeah, you can remove. If you don't need an electrician anymore, you just remove the electrician. That's done. Other people continue with their work. So yeah, that's another big advantage to using multi-agent systems. And lastly, we'll look at something called enforced compliance. Enforced compliance. Because you have multi-agents, you can easily build guardrails between how they interact, how they share information, and even how information is isolated. What information goes to where. So your business rules have become structural, not advisory. You don't have to go to your prompt and be prompting your agent to hell on what it should do or what it should not do. You can simply implement that within the structure of the system, so that it's either a possibility constrained with guardrails, or it's not just going to happen at all if you don't want it to happen at all. Agent A never sees agent B's information. Whereas in a monolithic system, when you have a single agent trying to do everything, each task is exposed to all the data for tasks that don't even concern it. So yeah, enforced compliance. Those are your benefits. So now that we've looked at benefits, let's also look at trade-offs. Take benefits here, and let us look at trade-offs. There is no perfect system. Every system comes with its own trade-offs. That is the whole world of architecture. So, what are the trade-offs to using a multi-agent system? What do you have to be aware of? What are the caveats? The first thing is increased latency. Increased latency. Okay, let me get that down a notch. So increased latency. Every agent transition is one more LLM call. Yeah. So all that moving around, all that information bus, yeah, that's just extra latency. Just like in microservices architecture. Or rather, just like in a microservice architecture. So yeah, increased latency, increased communication management and stuff like that. So you have to be aware of that. A single agent system is definitely going to be faster than a multi-agent system. Second, we have higher costs. Higher costs, which also kind of ties into the whole latency thing. So you get a lot of repeated calls. For example, in a sub-agent pattern that we're going to be looking at later, the sub-agent communicates to the agent, then the agent has to communicate back. The sub-agent communicates to another agent, the agent has to communicate back. So all that back and forth is going to cost you more tokens. So yeah, that's another thing to be aware of. Also, there's more complexity. Like I said, there has to be an information bus system where you decide how information is going to flow, how it's going to be managed. Also, you're dealing with different agents, so there's a lot of contracts amongst them that need to be fulfilled. Debugging becomes harder, and yeah, more failure modes, and even you have to manage a lot of consistency issues. So you are definitely dealing with more complexity here. Nothing comes for free, isn't it? So yeah, more complexity. Now, also conversation coherence. Conversation coherence. Now here, you have to manage the information in such a way that when each agent gets their task, they need to have everything they need for their task. In a pattern that we'll be looking at later called handoff, when one agent completes his work and hands off to another agent, the handoff has to be pristine in such a way that the new agent has everything it needs. It doesn't like miss any context. So everything has to be consistent. If you have a case whereby the whole flow starts feeling inconsistent to some agents. They will not know what to do. They will just hallucinate or just go off the tracks. So yeah, these are another complexity that you have to manage. You have to make sure that the conversation between your agents is coherent. Each agent understands what's going on. Each agent knows what to do, and each agent has everything it needs to do what it needs to do. So yeah, those are your trade-offs. But in a situation that requires a multi-agent system, this is totally worth it. This is totally worth it, because a bunch of situations are out there that you can only attack with a multi-agent system. So you should be ready to deal with all this. It's all part of engineering. So now that we've looked at when agents make sense and the benefits and trade-offs, let us take a look at what all this looks like in LangGraph, just from a very zoomed out level. What all this means in LangGraph. Framing, let me get this out. So what do we title this? Let's just say the graph abstraction. So the graph abstraction. Definitely could have given it a simpler name, but yeah, let's just roll with that. So the graph abstraction, what does it mean? How do these things, or how are these things represented in what we've learned so far in LangGraph? So first, nodes. Your nodes, what do your nodes represent? In a multi-agent system, your nodes represent your agents. They can represent your agents. They can also represent your functions, tasks, stuff you need to do, and they can just represent a particular computation. For example, in a pattern known as the routing pattern, there's a step where it just categorizes the task. So that's basically just a computation. Or you can also take it as a function. So yeah, that's what your nodes represent. Agents, they can be the agents themselves or the sub-agents. They can be functions, and they can just be computations. So that's nodes. So what about edges? What do edges represent? What do edges represent? Edges are simple. They are simply your transportation mechanism. So transition between agents, basically. So they do what they know how to do best. They help you move between agents. They are what you're going to use to determine the routing pattern that goes on within your multi-agent system. Next is state. What does your state represent? Say state. And state represents the information flow. Information flow between agents. Yeah. Your state represents your information flow between agents. Your edges represent your transition between agents, both your direct edges and your conditional edges. You can use your conditional edges to do runtime routing decisions. And your nodes represents your agents or your sub-agents, your functions, your computations, and all that. So yeah, that's what these core elements represent. Did I get everything? Okay, yeah, good. That's what these guys represent. Now, what about some other stuff that we know? Some other stuff we've worked with, things like checkpointing and stuff. For checkpointing, that's persistent with short-term memory. So checkpointing, if you want your multi-agent system to have memory between runs, which you most likely want, but sometimes it's just a single turn. A single turn can solve your task. Probably it's just a one-shot thing. It's just a one request thing, and it just runs through one turn and it's done. But if you're going to be coming back and you're going to be asking follow-up questions, you're going to be giving follow-up tasks, follow-up instructions, you want to make sure that your multi-agent system has a checkpointer. And the good thing about checkpointing in LangGraph is that it flows down. So once you give the main agent, if you give the overall system a checkpointer, it flows down to all the sub-agents. So checkpointing helps you to persist for long running and resumable workflows. Then we have command and send. Or let's just say command first. Command does what it does. You use it to update state within a sub-agent. You can update state within a sub-agent, and you can also use it to navigate to another agent, another downstream agent. So basically what we know about command, but in multi-agent systems it becomes even more handy as you can use it to dynamically update state and also dynamically navigate. And we have send. Send is going to be our main tool for parallel operations. So anytime you need to dispatch operations in parallel, anytime you need to dispatch tasks in parallel, you definitely want to use send. You want to use send. So that is what multi-agent systems look like in LangGraph. Now we're going to wrap up this video by looking at the different design patterns. This is not where we go deep into the design patterns. We're just going to discuss them because we can then look at each one later in full detail in other videos. But let us look at design patterns available in LangGraph for building multi-agent systems. So design patterns. Just going to briefly discuss them and get you excited about them. So the first pattern is sub-agents. In a sub-agent system, you have a main agent that serves as a supervisor and coordinates other specialists, which are sub-agents, to do their tasks. So that's basically what sub-agent does. It's very, very aligned with the whole innovation strategy. You are the main agent, you are the coordinator, and you're coordinating different specialists to do their job in your house. So sub-agents, that's your first pattern. Next, we have another pattern known as handoffs. The handoffs pattern. Now, what happens in the handoffs pattern is that when you have a goal and you know that goal can only be achieved by having different specialists, but you have a very sequential flow. One guy finishes his work, then he hands off to another one. That one finishes his own work, then he hands off to another one. That is where you use the handoffs pattern. There's no coordinator basically. One guy starts, hands off to the next one, and the next one picks up the task from there, continues, stops at the point, hands over to the next one. So peer-to-peer transitions. That's what goes on in the handoffs pattern. The next pattern is the skills pattern. And I'm sure you've heard skills a lot these days. There's a whole skills hype train in Cloud Code and some other AI tools all over X, Twitter, all over LinkedIn these days. So yeah, it's the skills pattern. Now the skills pattern is basically like a shape-shifting agent. It's actually one agent, but that agent has the ability to load different skills based on what you want. So it's like that G.I. Joe handyman actually. An handyman that has a lot of knowledge. He has electrical knowledge, he has plumbing knowledge, he has gardening knowledge, he has upholstery knowledge, he has even knowledge of POP. So when you want to do POP, it just loads POP knowledge. When you want to do electric work, it loads the electric knowledge. So that is what the skills pattern does, self-augmentation on an as-needed basis. And the last one is the router pattern. Which is specifically designed for you to dispatch tasks in parallel. Once the task needs to be dispatched in parallel, different operations running at the same time, not conditionally but by design, you use the router pattern. So what the router does is that it takes a goal, breaks it down, dispatches it in parallel, and synthesizes the results. That's basically what it does. Then you can always build a custom flow. We've learned LangGraph enough that you can build any type of graph. You can direct your graph in any way. So if your task doesn't fit into any of these patterns that we're going to be looking at in more detail later, if your task doesn't fit into any pattern, you can just go raw and design your graph from scratch in whatever way, or use an hybrid of different patterns, use your own custom flows, custom design, whatever you design flows here. So yeah, design patterns, that's the last thing we're going to be discussing here. Just as a quick bonus, I'm going to show you like a preview. I did a diagram of all these patterns, but we're still going to be looking at them later. But yeah, this is a preview of the different patterns. This is the sub-agent pattern, a coordinator giving tasks to different specialized agents and getting feedback. Handoffs, one agent handing off to another one. Skills, loading skills on demand from a whole toolbox. And the router pattern, which definitely splits tasks in parallel and synthesizes the results from the specialized agents that have worked on it. So yeah, this is multi-agents. This is your introduction to multi-agents, and from here you can pick this knowledge and start extending it through the lessons that are going to be coming up next.